Oh, let's see. Okay, these are bowerbirds. Now, bowerbirds are pretty cool. They're related to birds of paradise. They're all found in Australasia, so New Guinea, Northern Australia. Yeah.
That's the one that does a special mating dance, right?
Yeah.
That they spend like hours trying to get on video.
Exactly. In fact, I'm going to show you that.
Oh.
So, in fact.
But there's more to this thievery than brute force. Now, animal theft has become so sophisticated, we've entered the realm of organized crime. This male Australian satin bowerbird is only interested in stealing things that are blue for a very special client. The female bowerbird. This thatched bower is a seductive bachelor pad where the mood must be right for love. The male's pilfering is driven by the female's passion for all things blue. Visiting all the males in the neighborhood, she'll judge them on their home decorating flair. And it pays to accessorize. The more impressive his pile of ill-gotten gains, the more attractive she'll find him. This crime of passion may have started with feathers and berries, but we humans have made the haul much more varied. And the consequences more serious. So stay away from blue in the outback. And always remember that spare set of keys.
Yeah, so they go through this whole ritualistic dance. And you've seen this kind of thing before with a lot of birds and, very ritualized mating dances. And we'll look at that a little bit more later. But this is just one kind of an example. So I don't think, you think this behavior is learned or it's innate? Anybody? Might be both. There are some birds that actually do learn the dance. So there's these little mannequins that are there in South America. They display for the female on the left like this. They're very colorful. And for one species, the male, there's a primary male, and then there's a bunch of disciples. And so he's the one that gets to mate. But the more disciples he has, more attractive the primary male is. And then, of course, you're wondering, well, what happens with the subordinate males? Well, they're hoping eventually that maybe the top guy will get knocked off, and they'll inherit the territory. Or they may go out and establish their own. But it's the female is very, very picky, and as subordinate males, they actually learn. I mean, there's, I'm sure, a substrate in terms of that's somewhat innate, but then they modify it and get better and better at it over time. So we're back to proximate mechanisms and ultimate mechanisms again. I just want you to make sure you guys understand it all. So there's mechanisms, and then there's the development of those mechanisms. Those are proximate questions. They're questions of how. So if we So we're there, right here. Now, obviously, this is all tied together. So this is developmental environment, which we're going to be talking about later with the paper that everybody was assigned on the social life of genes. And then the proximate mechanisms, hormones and neural pathways, visual cues, sound cues, all that kind of stuff. Now, of course, ultimately, you have this ancestral environment, and then you have the evolution, function, and phylogeny. So, ultimately, you want to know whether a certain behavior is adaptive or not, currently adaptive, versus is it an ancestral trait that's held over from a most recent common ancestor. Okay. In fact, we're going to deal with that in a bit on, there's these fish eagles. You know bald eagle, but there's a whole bunch of them. And we're going to look at some behavior that involves phylogeny as well as perhaps current behavior. Okay. So we've gone over some of this: fixed action pattern, learning, conditional strategies, communication, all that. And then if you you go from highly stereotyped behavior to highly flexible, innate learning. So up here is something that is pretty much set in stone. Well, down here, we've got a very flexible creature, but of course you need, obviously, the phenotype for that creature to pull it off. Okay, how are FAP? Oh God, is that? Yeah. How are FAPs adaptive? Now, first of all, are FAPs highly stereotyped, or are they? Do they involve learning? What do you think? Fixed action patterns, like we saw earlier with, oh, let's just say yawning. Okay, is that something that someone has to learn, or is it pretty much fixed? Yeah. Okay. So now the question is, are FAPs adaptive? And you can look at things like egg retrieval behavior in geese. So the egg actually falls out of the nest. They go and retrieve it in a specific way. They don't have to be taught this. It's just a natural, an egg rolls away, that's the cue, the proximate cue. All the neural stuff goes on. It goes, oh, it doesn't even go that. It just automatically responds to the cue in terms of egg rolling it back into the nest. So there's nothing there except innate behavior. What's the good advantage of innate behavior compared to learned? What do you think?
Well, for instance, that, like if you had to learn that, and you had like say you had a bunch of geese that raised, the parents got killed off, they never learned that, they would be able to have offspring of their own.
Exactly. Okay. Also, what takes longer? Learning. So especially, let's say the fear response. The fear response is pretty much, I mean, you can learn to fear certain things, but the initial one, let's say, the monster comes into the room and everybody's terrified. You don't have time to think, oh, what should I do now? You have to respond immediately. And so, under those circumstances, or it's important that the organism actually responds immediately, then that's really favored for fixed action patterns. Courtship displays, like we just saw, a lot of those are fairly fixed. Okay, this is more wasp stuff. And it's pretty interesting. When I was giving up the movie industry and deciding to become a biologist, I went out to the Mojave, and we were doing a tortoise survey. But anyway, we stopped for lunch, and these wasps, like you saw before, they usually catch something, they immobilize it with a paralytic toxin. It doesn't kill it, then they lay their eggs on it. Which is the same sort of thing, but there's a little bit more to it. I was watching this one wasp, they're all specid wasps. A lot of times you can't really, they all look the same, a lot of them. So, but they all have a characteristic sort of behavior, as you'll see. And the only thing that's different is actually how they prepare the holes for their eggs. And you can usually see differences in terms of that. So I was following this specid wasp around because, I was really enthusiastic at that time. And all of a sudden, there's these two little flies that are like following it all around. And I'm going, that's weird. So, any ideas about why the flies would follow a wasp around?
Let the wasp do all the work.
What?
Let the wasp do all the work.
Yeah, good idea. So, this is these satellite flies are actually parasitizing the parasitic wasp. Okay, and what happens, as we'll see, but what happens normally when I saw it, the wasp got a crane fly larva, put it in a hole, dug it out, put it in a hole, and just about as she was going to lay her eggs on it, these satellite flies darted in and darted out and left their own eggs. And unfortunately for the wasp, they hatched first. And so it's an example of parasitic behavior. I don't know if it's probably a fairly innate response, obviously. I mean, these guys don't have big brains or anything. So it's got a larva, it's got a hole, it's dragging it down into it. Look at those flies that just came in. Did you see them? Hovering above, like bombardier pilots. Want to see that again? There it comes. You can actually even see the eggs dropping out. So, there's a lot of these kinds of behaviors, and this is an example of one of those fixed action patterns. And they all, let's close that off. And then on the other end, there's learning. It can be pretty simple learning, classical conditioning, or it can be something that's much more sophisticated, like what we do with language. The thing is to remember, it's never just genes or environment, it's the interaction between the two. So, with our learning, or any other animal's learning, they might have to develop it over time, and then do it properly. But there has to be the substrate, the neural substrate, there so that the animal can actually learn those specific things. So we have an area of the brain that's dedicated to language. And that's where all our language learning happens. Same thing with birdsong. Dedicated areas. So if an animal doesn't have that, obviously they can't do that behavior. So our learning behavior is really directed. And it's directed because it's important for our survival or reproduction. Oh yeah, this is where we all went off. Okay, so here's the classical conditioning again. Imprinting studies go awry. This guy is following ducks instead of the other way around. These are whooping cranes, and they raised them. They were endangered. All the cranes are endangered, but they were training these young ones. The flight route from their wintering grounds in Texas all the way up into the northern United States. And they did this because they had the bird's imprint on the guy who's actually in here. That's daddy or mommy or whatever, and they'll follow him anywhere. And he's using an ultralight, and it takes a couple days, and that's how they teach the birds. And then, of course, once they got it, and they're with the other whooping cranes, there's no more problem there. But they need that in the beginning. So there's really simple learning, and then here there's also much more complex learning. Okay. Now in birdsong, there aren't very many animals that are able to mimic. We're one of them. A lot of birds are. I'm trying to think. I think they found, there's this little primate in South America recently that they found. The young ones actually listen and learn and mimic the adults. So it's fairly widespread. In this case, just like with language, there's an early critical period. And there's this, what's called a species-specific template. So it's not like they can learn any old song. There's a substrate of song there, but it hasn't been developed properly, but it's innate. And then they listen to their fathers sing the song, and they start singing what's called plastic subsong. And they practice it over and over again. And then finally it's perfected and crystallized into song. Yeah.
There is this one bird, however, that can mimic any other bird
I
and
know.
any other unnatural sound, like a drill or something.
Yeah,
Like that. So how would you explain that?
It's got, there's a lot of mimics around. So we have one here, mockingbirds, and there's mimics, minor birds are mimics like that, where they can do all sorts of different songs, thrashers, and then the one you're referring to is the one in Australia. In fact, why don't we, okay. I think I talked about this earlier. Who's afraid of snakes? No one else? Poisonous snakes. Okay. It turns out it's really common in primates. Primates are pretty much obsessed with snakes. And you may think, well, not that many people die from snake bite, at least in this country, but it turns out snake bite kills, I don't know, 30 or 40,000 people a year. Or makes them lame, they lose limbs and all that kind of stuff. So, rhesus monkeys have the same sort of behavior towards snakes. And the question is, do they learn this behavior or is it innate? So, wild rhesus monkeys are terrified of snakes. They set up a video system, I explained it before. There's monkeys in the background, and in the foreground, they can put anything they want. A snake, a flower, anything. And then they have a young monkey who's naive. The monkey has never seen a snake before. And they play the video for him. So it turns out, if you just present a naive monkey with a snake, it doesn't really respond. Like, well, what is this? Okay? But in nature, their young monkeys are surrounded by mature monkeys, and those guys respond immediately. It turns out when young naive monkeys see wild monkeys respond that way, that's when they learn that in fact snakes are dangerous. And then old naive monkeys never really learn to fear snakes, no matter what. So, what is this, learning? Right? It looks like learning. But they did, instead of putting a snake in the front, they actually put in a flower. And they thought, okay, if it's all learning, the monkey should learn how to fear flowers if it sees the monkeys in the background going crazy over a flower. And it turns out the young monkey is wondering basically why these other crazy apes are going crazy over a flower. I mean, they're stupid. So it actually turns out that this behavior is both. There's an innate substrate in terms of you can do the same thing. Instead of a snake, you put like a long hose. The monkeys still respond to that. It's the shape. So in this case, there's innate stuff that's already underlaying everything. And then on top of that, monkeys are learning about their environment in terms of how to respond properly to snakes. Yes?
Was the naive monkey plucked out of the womb?
No. They were born in captivity.
So would it be safe to say that it already learned that the flower is going to be harmful?
No, so, okay. You have a bunch of young monkeys that were born in captivity. They've never been exposed to snakes before. Okay? The question is, how do they learn to fear snakes? By seeing a snake, they don't. But if they see other monkeys in their social group going crazy over the snake, so those are naive monkeys. A non-naive monkey is one that already recognizes a snake as dangerous. Does that answer it, or did you want something else?
My question was about the flower.
Oh, the flower.
So could it, so if it sees all the other monkeys going crazy, then it's just the snake.
Yeah, but it didn't respond to the flower.
It didn't respond to the flower.
Yeah, not at all.
Right, so it had learned in its captivity that a flower is not a dangerous thing.
No, the flower is actually the innate part. They need to see something that looks like a snake before they'll learn to fear it. That's the substrate, the shape of a snake. If they see a flower, that's not part, they don't recognize a flower as like a snake. underneath it all. So that part is innate. So when they see a flower, they don't respond. So it shows that there's both the innate part, which is recognizing a snake or something like a snake, and then there's the learned part. Okay? And of course, it's adaptive. Where is it? Okay, where's that thing? Shoot. Okay, I'll find it elsewhere. Okay. And then there's other kinds of learning too. One of the big things for a lot of animals, like learn with the wasps, is knowing where you are. If you get lost, obviously that's not going to be very good for your survival. And so a lot of jays and magpies and crows cache seeds all over the place. And what they have is a very well developed sense of spatial memory. So they can remember there might be thousands of caches, and they'll remember where most of them are. Rodents do the same thing. They don't seem to have as quite a good a spatial memory as some of these birds. And then the jays also, or the corvids, they are many times social animals. So when you're in a social group, it's really important to understand the social environment, or you're going to behave improperly. That's why if you go, let's say, to another culture, a lot of times something that you do naturally, they take that as an insult, or vice versa. Plus, we don't know who we can rely on, who are our most honest friends, and then who do we have to watch out for. And so this is called theory of mind. And the jays actually know they have theory of mind because they change their behavior when another jay is around. They'll make these false caches, and a lot of other animals do the same thing. Now, there's another thing. We don't know if it's really true, but
if you're a river otter in Yellowstone National Park, you're
a group slide. Here's a family of otters rollicking down a mountainside for no other reason than it's one heck of a lot of fun. These otters can reach speeds as great as 15 miles an hour on their way to the bottom. Human beings often pay hundreds of dollars to get into theme parks and go on rides that aren't any more fun than this. And Otterland is 100% absolutely free.
okay, so otters. Now the question is that really play? I mean, it looks like a lot of fun, but if you were going to write an operational definition of what they're doing, I mean, maybe when they're sliding along, they're actually thermoregulating or something. There may be other explanations for what they're doing. But it's been documented in actually not just otters, but a lot of animals besides humans. I mean, there's bears, there's ravens play, all sorts of different things. Okay. Now, these are blue-headed wrasse. And in this case, there's one male, and then there's a bunch of females. And all the females breed with the males. So we're going to talk about game theory and different strategies for actually whether it's evolutionarily stable, whether it's a good strategy or not. And the thing is, if the male disappears, the largest female actually changes sex and becomes a he. Bluegill do the same thing, except they do it in reverse. There's one female, a bunch of male, like clownfish, Nemo. So, in case you didn't know, Nemo was probably at one point going to turn into a female. They never said that in the Disney film, of course, because it doesn't seem exactly, But of course, these kinds of fish don't have this, men are from Mars, women are from, they get the whole side. It's not like, they don't understand the other sex. Unlike us. So, and also there's another thing going on here. There are different types of males. Usually you think, okay, there's a male, it's one sex. But there are males that actually play different strategies. One of those strategies is to look like, in this case, look like, let's see, what was it?
To look like a female?
Yeah, to look like a female. So you have the head male on the reef who's getting all the females copulating and all that, or laying eggs. But you have another one that comes along, it's actually a male, but it looks exactly like a female. It's a cheater strategy. So they come in and they inseminate quite a number of the females with their own sperm. Okay? So, and then there's other, let's see, what is it? There's, we'll talk about those later, but it's kind of interesting. There might even be, let's see, a lot of times there's another kind of male strategy where you mature earlier, like with salmon, and so you have two different sizes of salmon, full grown, and then the young one, the other ones that are small, but they get back up the stream in a year instead of 3 or 4 years. So these are sneaker males as well. They do the same sort of thing, and it varies in terms of how successful the strategy is. So with the salmon, there's a danger for staying out in the ocean for 4 years, obviously. Okay. There's also, when they're actually spawning, the big males are the ones that get to spawn. But it turns out you can have these jack salmon, and they play the sneaker game where they hide behind a rock near a female that's making a red. And while the males are duping it out, they shoot in there and do the same thing. But it only works if there aren't very many jacks, because there aren't very many hiding places as well. And also, so you have a fluctuation in populations of either jacks or full-size salmon. In fact, it's negative frequency dependent selection. So the more jacks, the lower your fitness. The fewer jacks, the higher your fitness. The more full-size salmon duking it out, the lower your fitness. And then the fewer, the higher your fitness. So it goes kind of back and forth. Yeah.
Do you ever change strategies, or is it kind of set like that?
It's pretty much set. But I'm not exactly sure the whole genetics behind it about, but part of it has to do with the social environment. And it might have to do with the female. So either strategy can be beneficial depending on the right context. Okay. So, let's see. A equals B. Okay, B's that one. Okay. So this is B, and this one is A. And then, in terms of individual status, so this graph shows the fitness payoffs of phenotype A and B in relation to an individual's status. When they're low status individuals, it's better to be B. Fitness of phenotypes. Okay? Now, when your status goes up, it's actually better to be A. And then there's this point right here where the lines cross. So let's see what it says here. At the intermediate point S, the fitness benefits in A and B are equal, and either phenotype may be expressed. So individuals of higher status above points S will receive more fitness benefits, more from exhibiting phenotype A, while those of lower status will achieve higher fitness with phenotype B. So it depends on the context of the situation and the kind of hierarchy that you have in the social group. And we see this all the time. I mentioned these little birds in the Middle East called babblers. The dominant individuals feed the subdominant individuals and not the other way around. So most of the time, only the highest status individuals do most of the breeding. But you don't see a low individual like giving a high status individual food. This doesn't work that way. So it really depends. The same sort of thing happens when we'll do the hawk-dove game. You have a mix of you're either a hawk or a dove. If you're a hawk, you fight. If you're a dove, you flee. And the fitnesses of both depend on how many hawks there are or how many doves. Same sort of thing. Let's see what happens again. Okay.
A lone eagle has come to check out the fishing.
Okay. The thing is, they also use it for something else.
Yeah, bald eagle. Biol, we all got one 5 months ago. It's got a lady friend. Of all courtship rituals, none is as spectacular as that of the bald eagle. The male and female climb to dizzying heights. And then join in free fall, plummeting towards the earth, locked in each other's embrace, separating only at the very last. Yeah, bald eagle. Deal. We all got one 5 months ago. It's got a lady friend. Of all courtship rituals, none is as spectacular as that of the bald eagle. The male and female climb to dizzying heights, and then join in free fall, plummeting towards the earth, locked in each other's embrace, separating only at the very last moment. Gotta miss Edith. Yeah, I gotta miss Jazz.
Okay, so we've got the same kind of behavior used for two different things. Now, I'm not sure which behavior, or the reason for the behavior happened first. Let me go back to this. Okay, so I'm just going to draw a little phylogeny. Okay, so we'll say this is this group is the group of all the sea eagles, and from this point on, well, actually, we'll say that's the most recent common ancestor for the whole group is right here. Okay, so now the question is, we can map character traits on this phylogeny. Perhaps we have to know whether this is a phylogenetic behavior, in other words, ancestral behavior, or whether it's actually adaptive now. So it could be that they all did this, the whole group, and their common ancestor did this for dominance initially. And it was only later, let's say from this group on, that it was then usurped to use in courtship displays. So what we want to know is basically, when is it a phylogenetic effect and when is it actually an adaptive effect for the lineage that you're looking at? And this is called the comparative method, and we're going to be kind of getting into it different times. But it's important, if you remember Tinbergen's 4 questions, the question is for ultimate, is it adaptive now, and or is it an ancestral behavior? And you want to be able to distinguish between the two. So if a whole group has this behavior for dominance, then we'll say, and that other groups don't, then we'll say that the whole group, the behavior started at the beginning of where the whole group split off from the common ancestor. But if, let's say you have another behavior up here at the tip, another kind of behavior, then we can say, and we're looking at, in terms of behavior and clades, we can say Okay, so this one has it, and this one doesn't. And that's an example of actual adaptive evolution currently. So from this clade on, A has this behavior and B doesn't. Okay. We're going to get into hormone mechanisms more, but things change over the year in terms of sex. Unlike humans, which are able to have sex all the time, females are always receptive. Other animals, females go into estrus at certain times of the year and not in others. And then, if we actually look at this, here we have sexual size. So this is the male, and then this is the female. So February, right around February, things start to change. The testes size, or the sexual organs, increase from then on. Here's the breeding season, and then of course, right around there is when, August we'll say, is when the breeding season stops and their sexual organs shrink in size. Now for birds, this is really important, if you can imagine, because carrying around large testes, or the bird is full of, the female is full of eggs, producing eggs. Those things are heavy. And so you see these kinds of changes so that at the start of the breeding season, these things get more important. They produce eggs and sperm and all that. And then later on they shrink down, especially if these birds are migratory. So they don't want to be carrying around all this extra weight when they're migrating. And these things are affected by hormones, and a lot of times it's the cue is either how much light there is in the day, or the angle of the sun, depending on what it is, perhaps the temperature outside, that starts these changes happening. And then it's all controlled by hormones. Let's see. Okay, now this is, let's see, look at this. Okay, percentage of females with mature follicles. And in terms of when they have the most mature follicles. So when a female is completely paired with a male, she's producing the most follicles. If a female is with a group of males, they start a little bit later, right around here, and then reach up to here. But these females with let's say a group of castrated males, or all female group, or female alone, they all produce fewer follicles during the season. Now this can also be mediated, by the way, in terms of, let's say, the food environment. If there aren't enough resources, they won't breed at all. Okay, so we have all these different modes of communication. Yeah. Oh my God, we got that far? Only that far? Okay. We'll switch gears now and go to the